Hello, we will be talking about this problem. A 5 ampere current runs through a 12 gauge copper wire, diameter 2.05 millimeters, and through a light bulb. And we know that copper has 8.5 times 10 raised to 28 free electrons per cubic meter. First question is, how many electrons pass through the light bulb each second? Let's focus there. We're looking for the how many electrons. So our given 5 amperes, diameter, 8.5 times 10 raised to 28. How do we deal with this one? Firstly, we must know that if we're looking for the number of electrons, we don't have any other unit aside from the number of electrons. It's just a discrete number. So firstly, what do we have here? We've got our I given 5 amperes. We've also got our diameter, 2.05 mm. I think my pen is too thick. Let me redo it. Okay, excuse me, sorry. I is equal to 5.00A. D is equal to 2.05 mm. We've got here 3 electrons. 3 electrons equals 8.5 times 10 raised to 28 electrons. So that's basically the number. Now we've got to also note that we have what we call I, which is your amperes, equals to your Q, our charge, divided by your time. So that is charge per time. That's the rate of charge. All right. And we know our I, but we don't know our Q. So manipulating the equation, we'll be able to get Q is equal to I times your time. And your I is 5 amperes times your time. Let's say 1 second here. That would give us 5 coulombs. 5 coulombs. Since we're looking for the number of electrons, we need to say, note again, we need to know that it'll be, I have a number of electrons times my electrons. So E is the charge of your electron. Now, we're looking for the N. N is your number. So that is charge over our Q a while ago, which is 5C, divided by the charge of electron. And substituting, our Q is 5C divided by our E, which is, by convention, 1.6 times 10 raised to negative 19. That's the magnitude. After which, we can get 3.125 times 10 raised to 19 electrons. So how many electrons pass through the light bulb each second? There are 3.125 times 10 raised to 19 electrons pass through the light bulb each second, so electron per second. Next one. Now we are dealing with what's the current density in the wire? Looking for the current density. And remember, current density is denoted as J. Current density is denoted as J. So we're looking for our J here. What is our equation for J, or our current density? Note, current density is equal to your ampere, or your current, divided by your area. Area is a cross-sectional area of the said wire, the copper wire. Now, we've got our diameter here, and most likely I always tell the class, if you've got diameter, you can, of course, convert it to M, and then diameter have the R, because the formula for your area basically is with of course you can have diameter, but it's simplified when you have R. R is like the SI if you're dealing with R versus D. So R is equal to D over 2, which would give us 2.05 mm divided by 2. Okay, so let's see here. R is equal to 2.05 times 10, I'm converting, negative 3m divided by 2. That would give us times 10 raised to negative 3m. That is our radius. Now to get the area, we know it must be pi r squared, or pi d, pi d, yeah, in this case, you can have the d, but remember what would it look like? Okay, it's not really pi d. So pi r squared, pi is 3.14. Well, just have the pi in your calculator then. So pi is constant. Your r is basically 1.025 times 10 raised to negative 3 squared. Your area is 3.301 times 10 raised to negative 6 square meter because it's an area. Now, we've got our I. Let's focus on getting our current density. So our current density would be 5 amperes divided by 3.301 times 10 raised to negative 6 square meter. That would just give us 1.515 times 10 raised to 6 amperes per square meter. Okay, but let us see at what speed does a typical electron pass by any given point in the wire. But look for the speed here. At what speed? So think of the variable involved in speed. That must be v, or your velocity. Now, as you know, we've got here a current. We've got here current density. What we do remember when we're dealing with current density and velocity is that it's not simple speed. It's what we call drift velocity. It's not just a simple velocity. So it has to do with your drift velocity, which is your VD. Excuse me, it must be a small v and smaller d. So that is what we call drift velocity. Now, if you do remember, we've got another equation for your current density, which is J, again, current density, is equal to NQ VD. VD is your drift velocity. Now, we're looking for the VD, we're looking for the V here. Manipulating the formula of the equation, you must have your VD is equal to J over N Q. Now, we already know our J a while ago. That is 1.515 times 10 raised to 6 ampere per square meter divided by your N. And a while ago, the given, which is 8.5 times 10 raised to 28 free electrons. So just copy that. Free electrons. Okay. Times your charge here. This is an electron. Okay. I forgot to mention that this must be an absolute value. Absolute value. So the absolute value of this is an electron, negative 1.6 times 10 raised to negative 19 coulomb is just the positive of that. So making easy operations, you'll get 1.114 times 10 raised to negative 4 m over s. This is your drift velocity. At what speed? Okay, this is your v. And lastly, if you were to use wire of twice the diameter, which of the above answers would change? So we're looking for which of the above answers would change, and would they increase that system or decrease? Let's analyze this. Okay. So which of the above answers would change? Now, if we're dealing with a diameter, the only way to see the diameter is by having the equations that we had a while ago. So what did we have a while ago? Current density is equal to I over A. That's number one. Number two, we also had the drift velocity. Drift velocity, J and absolute value of K. For number three, we also had the drift velocity as well, equals your I, your current, divided by your N, absolute value of Q, times your A. There you go, times your A. Now, as our diameter, because twice is 2x, so this is increased, not even half. So as our diameter increases, the area would increase too. As our diameter increases, the area would increase too. So the current density would decrease. If the area is increasing, as you can see here, let me grab another pen. If the area is increasing, I expect my drift velocity to decrease, similar to this one. If my area is increasing, this one would decrease, satisfying the equation J is equal to I over A and or VT is equal to I divided by MQA. So that's it.